Much everybody for coming. I think better Tito make the honors today, yes, since you know her much better. So yeah, it's my pleasure to introduce you Güzin Bayraksan, which I'm most certainly mispronouncing the name.
It's pretty good.
Okay. So well, I've known Güzin for a number of years now. Ever since she was a PhD student at the University of Texas, Austin, and she was working multi-channel methods for stochastic optimization, which is a topic that is very close to me as well. So we've been meeting conferences ever since, and I think back from 2010 we have been also collaborating quite a bit together. And last year I visited Columbus, and now she's visiting us, and well, she's been growing quite a bit as a researcher, has made an excellent name for herself. Have won the career award in the US. She's treasurer for the Committee on Stochastic Programming. She's the president of the WORMS, which it turns out to be the Forum for Women in OMS in the United States. She's very active in that regard as well. And she has been doing some excellent work related to stochastic programming, more specifically, more recently on data-driven stochastic programming, which is what she's gonna, and also a nice application to water allocation. So you've been involved with that for a number of years, right? On the water stuff. Like
yes, yes.
I think you tell us about that.
I'll have it at the end of the presentation.
So anyway, I'll let her present the work.
All right. Well, thank you very much. It's a pleasure to be here. Beautiful campus. Love it here. So. Anyway, today I'm going to be talking about data-driven stochastic optimization, and I don't know if you've ever heard of them. Something's called Phi-Divergences. Some of special cases you might have heard. I'm going to define them. So, and then we have an application to the water allocation problem in water-scarce region, specifically Arizona, with my collaborators there, and my former PhD student David Love. This is joint work with him. So I'm going to start with introduction and motivation. Why do we want to do this problem? What are these Phi-Divergences? What's the formulation and basic properties? And then I'm going to talk about some data-driven considerations. So what happens is we keep collecting data, and we have a specialized decomposition algorithm and a classification of these Phi-Divergences, and an application at the end of the second half, or last 1/3 maybe, of the talk. All right, so please feel free to stop me whenever you have a question. All right, so obviously deterministic optimization, I mean, it's still a very active research area, right? There are some problems that are so difficult to solve, and typically, even though there are uncertain parameters in the problem, you assume some expectation or just say demand is this, and you try to solve that problem. So if you've got a very complicated integer program, right, you just try to solve that problem. Yet again, there is a lot of uncertainty in the real world. So it's another step is say, hey, I don't know, I'm not going to say pretend it's deterministic. I'm going to say there's some kind of a distribution, different scenarios that could happen. I'm going to put a probability distribution around it, and I'm going to try to solve the optimization problem, say, by minimizing the expected cost. All right? And so this is one way of dealing with it, but there's another problem, because in real world there is typically data, sometimes not even enough data, but there is now especially data, but there's not the distribution, right? Distribution is something people just put on it to explain it better and have other properties. So if we can collect data, it could be direct observations, right? So if you have a system that's already in place and you can do this sequentially, you can also simulate. So you don't know exactly what's going to happen, but assume this happens, assume that happens, and you simulate it a little bit. You tally the simulation results, so you collect some observations. You go talk to the experts. They tell you, in the future, this might happen. No, I don't think this will happen, right? They can give you some plausible scenarios. So you can use all of those, and then typically the way, especially if you have direct observations, you tell them, say this is a histogram, and you fit a probability distribution here, and you put it in your optimization model, right? But there are problems with this. Some cases it works well, but some cases there may be not enough data. It's a new system. You don't have enough data. What are you going to do? You can collect expert opinions. You can, do some simulations, but you don't know. Right? This is a second one. And then sometimes there is actually a lot of data, but there's not that much trust in the data. So water problems that I'm working on, these earth scientists, they use a lot of stochastic differential equations. They do huge simulations. They simulate what's, the cloud coverage around the earth. And then they predict 40 years, 50 years down the line, and they have these statistical models where they turn the Earth's global circulation models into like 100 kilometer square area in March of 2025 on, 25th of March, we expect this much rain, temperature is going to be this. And then there are many different models like this, right? And there are some that are more trusted. There's a Japanese group, there's like a European group, there's several American groups, Australian. There are many of these models. And you can get actually this temperature, precipitation, etc. from these models. So you have a lot of data for future predictions, yet you do not really trust them that much. Because there are so many errors that goes on in the global model, and then statistical, they call it downscaling into its particular area. There are precipitation bias issues. So you have a lot of data in some sense, data points, but you don't trust them. So in these cases, there's ambiguous stochastic is one word, or more recently, like distributionally robust is used a lot. So you don't know the distribution, so you want to hedge against the uncertainty in the distribution, right? So you consider the uncertainty or ambiguity in the probability distribution explicitly in this case. And this is not a new thing by any means. So one of the earliest results is like from 1958. So mean robust models. So you say like, I'm going to consider all distributions with a certain mean variance, or certain moments, right? But obviously, there are many distributions with the same moments. It doesn't tell you enough. It's too conservative if you just use, and this turns into some minimax approach. And this is again from the 60s, going back to 60s and some earlier results. Chance constraints, you can, there's a lot of work on this. There's actually new papers just came out, right? 2 days ago, 1 day ago, something like that, right? Yesterday. So there's a lot more work that's going on here. So it's just a sampling of it. There are different ways to create these ambiguities. As I said, considering all distributions with the same mean and variance is one way. But if you talk to a statistician, they will never like that, right? It's not a good way to do it for a statistics perspective. If you can use any distributional information, if you've collected it, it's much better, which would be, for example, Phi-Divergences do that a little bit better, right? So in earnest, I'm going to say like Bentald 2013 is the management science paper, is a first sort of paper that, specifically considered Phi-Divergences in this context, right? And so we're going to take their work and sort of expand on it. All right, so what's happening here? We have a bunch of assumptions. One of them is we're going to only focus on, in today's talk, discrete distribution. So discrete and finite, right? So we have a finite number of realizations. And these are sort of probability measures. So like different scenarios will be indexed by omega. And we have n of them, the small n. And so this is the probability of scenario omega, probability of scenario omega under distribution Q. So Q is going to be our nominal distribution. So this is what we can get from our data points, simulations, expert opinions. And when I say distribution, so like these look like probability mass functions, but we allow them to be 0. So it's not necessarily greater than 0 for that particular scenario. Right, so you might not have observed one particular scenario, you can have 0 in there, or vice versa. All right, so phi divergence is a measure of distance. It's not really a distance, but it's somewhat like a distance between two distributions. You give me P, you give me Q of, say, 5 different possible futures, and one of them will tell me it's like equal probability. The other one will tell me, a lot less here, a lot less there. In the middle, there's more probability, And then you say, what's the distance between them? Right? There are many ways of doing this, and Phi-Divergences is just one way of doing that. So what it does is, this is a nominal distribution. So you can think of it as you're taking an expectation with respect to the nominal distribution of some function phi here of these ratios, right? So if, for example, P is equal to Q, they give the same probability to the same scenario. The distance between them should be 0, right? So if they're the same, so basically this phi function has some properties. If the ratio is 1, then the distance is assigned to 0. And very nice property, that phi of t for, positive here, is going to be convex. All right? So this actually makes our life a lot easier because you're going to end up with convex optimization problems. So you don't have to deal with non-convexity here. And then there are some special cases, as I said, you might not have observed some data, so this might be 0. So in those cases, there are some definitions that, so basically the terms here are defined like this. And if they're both 0, then there's no distance between them, so it's set to 0. And so this is actually Phi-divergence is more general. You can give any two vectors, look at the Phi-divergence between them. But when we consider probability measures, these quantities must sum to 1, right? So in that case, we can, without loss of generality, assume that this phi function is always non-negative. Okay?
I can start from any function phi that
exactly.
satisfies phi properties. I can use phi.
Exactly. Yep. So we can create Tito's phi divergence, right? Which we actually did. We wanted to see this risk measure, so we ended up creating our own special phi divergences that satisfy these, and we got like some, very commonly used risk measures, for example. All right. So as I said, they're kind of like distances, but they're not like metrics. They do not all of them satisfy triangle equality. Most of them are not symmetric, right? So it doesn't have this like a regular distance type of, or a metric, right? Or not semi-metrics even. So especially this symmetry issue, you can define an adjoint, right? Which is defined in this manner. And the nice thing about the adjoint, so we put a tilde here. So if you change the order of these two distributions, P and Q, Q and P, then the adjoint will then be equal to the phi divergence itself. Okay? So if they are symmetric with respect to the P and Q, then they're called self-adjoint. All right? So there are many of these, and they're commonly used in statistics, actually in computer science, artificial intelligence, machine learning. These are very commonly used. Right? Oh, another thing that's going to show up a lot in this is the conjugate function. So it's the convex conjugate of the phi divergence, right? And we're going to use its properties quite a bit. All right, so here are some examples. Some of, I'm assuming some of you must have heard this is one of the most famous divergences. Kullback-Leibler divergence is one of them. Its adjoint is the Burg entropy. So you just essentially almost the same. You just replace the negative kind of thing, and then this is the phi divergence. This is the phi function, and this is the conjugate function. So sometimes the conjugate does not have a closed form, and sometimes it's like infinity, say when s is greater than or equal to 1. So it's defined on its domain, effective domain. So again, chi-squared distance, modified chi-squared distance. The chi-squared test, right? Between two distribution goodness of fit tests. That's basically related to these, right? So you look at the expected, observed squared, divide by expected. You create your chi-squared, test statistic. So, right? And so these things actually can be used to create goodness of fit tests for distributions, for data, right? More than just the chi-squared, Pearson's chi-squared test. So this one is, right, this is the norm, L1 norm, Hellinger distance, and there are many, many more. Yep.
General question.
Yep.
Are those, of course, they are divergences, so they satisfy the properties.
Mm-hmm.
Were they proposed because they highlight some aspect of the proximity between the distributions? Why would one pick one from those from the library for a specific problem? Is there an answer to that?
That's exactly the question we had, especially in optimization. So that's like we came up with the classification. But I think these things have a history, like the chi-squared distance modified chi-squared. They're like tests. Cool, but
statistics,
Yeah, statistics mainly, and then also information science, some computer science people added on, and I think this just combines them.
But they also characterize this convergence probabilities. They're not equivalent.
They're not equivalent, no, but it depends on what context you're looking at them. Yeah. So they have differences, right? I mean, and this one results in like nice models, is nice fastest rate of convergence kind of thing. So people use this a lot, for example. So they have like different type of properties, but still it's an open question, right? Especially if I use it in the optimization context, and this is only a subset, right? There are many more. And then which one I use and why. So, and that's the classification we try to come up with, at least some ideas of like to guide the users on this one, which I'm going to talk about in a while. All right, so formulation, basic properties. I assume everybody's familiar with stochastic programming or two-stage stochastic programs with three cores. Yes, no, maybe? I mean, I guess, I'm looking at the students. He's like doing this. I should be. All right, so just quickly, right, I mean, again, our big assumption here is we've got a finite, number of realizations, and then, again, this is our nominal distribution. Usually, this is a typical two-stage stochastic linear program. The uncertainties are going to be in these parameters here, maybe the bounds on the second stage decisions. And you want to minimize the first stage cost plus the expected second stage cost, right? So if this is a probability distribution and you know it, this is your expected second stage cost, which comes from the optimal value of solving a linear program, right? And the first stage is kind of like a linear program on its own. Obviously, this part is convex. So now what we're going to do is, very typical way, you collect data, and you say, okay, if I've observed 5 of this scenario omega out of 10, I'm going to assign 50% probability, and however many I observe, I'm going to assign that much probability, right? And so you can just basically stick the empirical distribution for your known distribution, and that's going to give you, or you can do this by Monte Carlo sampling, right? It's the same idea, sample average approximation, right? Now what we're going to do is, instead of considering this nominal, what we call nominal distribution, we're going to create an ambiguity set of distributions that are centered around this nominal, right? And we're going to use Phi-Divergence to do that. Oops. All right, so ambiguity set is this Kelleographic P, and this is what we call the Phi-Divergence constraint, right? It says, look, this is my nominal distribution, but I'm going to consider all probability, distributions on this set of scenarios, P, that are sufficiently close to Q with respect to a phi divergence. And sufficiently close is determined by this rho, all right? And then obviously I have to have, this is a probability measure, so it has to sum to 1, and they have to be non-negative, right? So those are your other constraints. So you consider all of them that are sufficiently close. And then in the end, instead of solving, minimize the first stage cost plus the second stage expected cost, now you have distributions that come from that ambiguity set, and you do a minimax. You, instead of the expected cost with respect to nominal distribution, you do expected cost with respect to the worst case distribution from that set, right? And again, that set is this, is a convex set, right? Ambiguity set that's given by this. The X is the first stage feasible region. These are the optimal values of the second stage problems for each scenario omega. So same setup, right? But we have a min-max problem now. All right. So one big question is obviously how to determine that rho. And again, if you don't remember, the rho is like, how close am I going to stay here, right? If I have some observations, should I remain really close to it, or should I remain far away from it? So one statistical answer to this, there's a chi-squared convergence result, actually, of the phi divergence, if you collect the empirical distribution. So if you use the empirical measure as your nominal distribution, and you have this differentiability condition here, and this second derivative at 1 is greater than 0, then there's a chi-squared convergence result. The phi divergence normalized in a certain way will converge to a chi-squared distribution with number of scenarios minus 1 degrees of freedom, right? So this comes from statistics or Bipardo's book, right? And if you do some a little bit changing and using this chi-squared convergence result, by setting this rho to be this value, you ensure asymptotically that your ambiguity set will contain the true distribution with, say, 95% probability. Okay? So, and the thing to note here is n is your total number of observations. So if you have a lot of observations, you're going to remain close to your distribution. If you have few observations, you're going to have a larger ambiguity set, right? And it kind of makes sense. As I collect more data, and if there's a true underlying distribution, I'm going to get closer and closer. And this is 1 over n, sort of, you shrink the ambiguity region of order 1 over n. All right. So just to give an example, so if you've done statistics or even any statistics that you use, everybody uses maximum likelihood estimation. Even when they don't realize, they do maximum likelihood estimation, right? So this is, they came up, actually, Peter Glynn and Ying Yu at Stanford, right? They came out with the likelihood robust optimization, and Hu and Hong used the Kubat library. It's a little different, almost the same, but so they use the empirical measure, and then they say, look, they write an ambiguity set like this, but it's saying this. So this is a normalized maximum likelihood estimator. So if you collect data, maximum likelihood estimators for any scenario is number of observations divided by the total number of observations, right? So, and you can calculate that easily. This one is a normalized one. So it says, instead of considering maximum likelihood estimator, I'm going to consider all distributions that are larger than, say, 80 or larger than, or at least 80% of the maximum likelihood estimator, right? Not only the concave function that you maximize there, but anything that's about 80% of the maximum likelihood. So, so 0.8, this would be 0.8. And then when you do that, this is basically equivalent to, this is the empirical likelihood. So you consider all distributions that are greater than or equal to some number here, sufficiently large likelihood instead of the maximum likelihood. All right? And again, when you use the chi-squared result, you basically set this normalized likelihood parameter to be this e to the chi-squared with some degrees of freedom and stuff like that. All right? So you do this, you basically, instead of using the maximum likelihood, you consider all distributions that are sufficiently high likelihood. And here's what's happening in practice. So this is some simulation with two scenarios. The original distribution has the first scenario 40%, second scenario 60%, but you only need the first one. And we basically did like generated 10 observations. And then only one observation turned out to be from the first guy, 9 observations from the second scenario. So this is a likelihood function if you plot it. And the maximum likelihood estimator obviously is 0.1, all right? But you say this row, you set that row so that you're approximately 95% confident that your distribution contains the true parameter. When you do that, this is your row value, so to speak, okay, or gamma bar. And so instead of using 0.1 as your maximum likelihood, this optimization problem will say, my P1 will change from 0 to, say, slightly less than 0.4. So it considers all of those. But you can see it doesn't have the true distribution. So there's still some error probability here, 5%. All right, so as you collect more data, add 50 more data, now you see the maximum likelihood estimator is really close to, a lot closer to 40%, the actual number. But now you say, oh, it's going to be between these two, instead of considering only that maximum likelihood. You add more data, you get closer, and so on and so forth. All right, that's how it's going to work. All right, so some basic properties. It's the resulting problem, the minimax, is a convex optimization problem. Furthermore, it's equivalent to minimizing a coherent risk measure. And if you know coherent risk measures, there's a dual formulation, right? So it's the minimax coming from a distribution. So it's exactly that. So in the end, you're essentially minimizing, instead of the expectation, you're minimizing a risk measure. And that risk measure is dependent on, first of all, the row, how close your ambiguity region is. And 2, it depends on the specific phi divergence you use. So by changing the phi divergence, you change your risk measure. And then it's actually, you can reformulate it, and same structure as the stochastic, two-stage structure remains, so you can do decomposition algorithms and stuff. And to do that, take the dual of this problem. So here's the primal formulation, just I'm writing the max part, so there's the min-max, right? So the max part given this phi divergence ambiguity region. Then this is a dual variable for the phi divergence constraint, right? That will show up in the dual problem. It has to be non-negative, this, that. So if you basically use Lagrangian dual, and there's some special properties of the conjugate function, so it's going to show up with a conjugate here. Mu is going to show up there. The feasibility, so the conjugate is not always the effective domain of the conjugate, right? So sometimes, for some phi divergences, you also have this feasibility constraint. Okay? All right. And also the conjugate relationship will give you the relationship between optimal and primal duals. We define this S omega like this, second stage optimal cost for a given first stage decision, mu lambda, and then it's going to belong to the subdifferential of the conjugate at that point. And if you have some, many of them are differentiable, so you automatically get that easily once you solve the dual problem. All right. So we looked at what happens as we collect more data. So this is one of the things we examined. One thing we said, okay, what if we collect one additional data, right? Then what happens? And the thing is, so if I say I observed scenario K, now scenario K had NK observations, now I'm going to add one more to it. Can I just say the optimal solution will remain the same, or the optimal solution will change, under what conditions, and things like that? And so we looked at basically using the convex optimization problem properties, not that hard. So you can actually, if you use empirical distribution, you keep collecting data, and you solve your problem with total n observations. Now you observe one more from scenario K without resolving the problem. If you check this condition, if this condition is satisfied, then you know your n scenario problem is going to change. So you no longer have that worst case optimization. You're going to have a better objective function value because you became less conservative. You collected one more data, you became less conservative. This is that condition. It looks complicated, but you can specialize it for different phi divergences. So for example, the likelihood robust optimization one, actually this is what we started with and then did the general case. But so the likelihood robust optimization one says, look, this is my empirical observation. So say I had 5 out of 10 observations. So my nominal distribution gives that scenario K 50% probability. But I solved the minimax, and the minimax gave it, say, 30% probability, something like that. So you just check this very simple condition. So n plus 1 over n. If this is the maximum likelihood, this is the worst case distribution. If the maximum likelihood estimator is slightly larger than this n plus 1 over n of the worst case distribution, you will actually rule out the current worst case distribution and have a better solution. Okay?
So you have to recalculate to get
yeah, you do. So this only tells you it will change for sure, but it doesn't tell you what it would be. Yeah. Yeah.
If that condition is not satisfied, then I know I can keep this.
So if that condition is not satisfied, it might change or it might not change. So we did some, empirically checked it. It's only one direction. Yeah, unfortunately. So, but if it doesn't, it's not satisfied. Sometimes it does also, rule out the worst case distribution. But most of the time, it worked fine for the problem that, problems that we checked. Yeah.
What happens with the region of the distribution?
The ambiguity, you also shrink it just a little bit, right? Yeah, so if you add one more data, you're going to have that chi-squared, the n thing, so that there's 1 over n plus 1 instead of 1 over n. So it's all considered in it, yes. But it's a tiny bit, right? N to n plus 1. So one more observation, yes. You shrink the ambiguity region as well. It takes that into account. All right? So, I mean, this is basically a good scenario. Like, if you know if this condition is satisfied, this is a really good scenario. So, if you collect one more observation, your belief in that scenario increases, and that makes you be less robust. So, it's a lower cost scenario is actually satisfied us in the end. All right? Because the max tries to give higher probability to the worst case ones. Right? And you can do this for other ones. Once you solve it, these are not that hard to check, so you can specialize them for different Phi-Divergences. All right, so here's another result. What happens is we keep collecting data instead of just one more observation, right? So we wanted to examine this. So we're going to, when the Phi-Divergence function has a unique root at 1, right? And we either select this ambiguity row, the level, using chi-squared result, or somehow we shrink it, say, by 1 over n. And X is compact. We have relatively complete recourse, second stage dual feasibility. So we don't have these infeasibility type of issues. And we know we're going to have convergence in the X's and things like that. Then you can show the robust version of this problem converges, the optimal solutions converge to the stochastic linear program with the true distribution. All right, and then the optimal solutions will become the limit points of this. Optimal value will converge to the same thing. So it's basically becoming a two-stage stochastic linear program with recourse with the true distribution, right? As you collect more and more data. All right. You can also decompose this as I told you, and you just use the convexity. And the only complicated thing here is the some Phi-Divergences has a feasibility constraint, which is a nonlinear constraint. So this is a dual, the full dual problem. So it's a first stage decision, dual variables lambda and mu, and this is the conjugate. This is the second stage optimal objective function values for a given scenario and for a given first stage decision X. This is the feasibility constraint. Again, not all Phi-Divergences have this, but some will have it, depending on their how their conjugate behaves. This is the first stage feasibility. All right. So what we do is this is a convex function, and we replace it by objective cuts. Essentially, it's a convex function. I'm going to replace it by theta. The cuts are a little bit slightly more complicated because you not only have the x now, but you have the dual variables lambda and mu. Use the chain rule, take subject derivatives or differentials and stuff, and create cuts like this. The thing, excuse me, the thing here is you have the conjugate of this sort of optimal value of a linear program. So instead of doing the nonlinear, sort of this convex function, right? So instead of using that, we basically solve this, take the dual variables, and then translate the dual variables to the subderivatives of the conjugate. All right, so we end up solving linear second stage problems. So we don't have to solve convex second stage problems. So that's number one. And the first stage, if you don't have this constraint, is a linear, again, master problem. If you have this constraint, then what we do is we basically take it out and add feasibility constraints after solving this. If there's a violation, we add, again, linear constraints to get rid of these infeasibilities. So in the end, we end up solving a linear second stage subproblem, linear master problem, add the feasibility cuts when needed, sort of re-optimize, get another mu, and then continue. All right?
So the function is two convex non-derivatives, right? X lambda and mu. The phi star is always
This one? Yes. Yes.
Phi star that's two.
Yes, it will go through. There are some weird cases when lambda equals 0. So that's a weird case. But 1 over lambda, when lambda is positive, right, it's going to be with the phi star non-increasing. Look, yeah, and then so when you do the composition, it's still going to give you a convex. Or you can just directly show it from like the definition of lambda 1 plus lambda 2, like theta 1 minus theta. You can do that and show the convexity as well. Yeah, like numerical issues when lambda is equal to 0 is a something. So that's a bit of a tough one, but other than that, it works. All right, and so just to sort of solve the first stage, which is basically the master problem, and then send the x's to the second stage problem, solve them, get the duals, and check feasibility. If this is violated, generate the feasibility cut. Well, I think there got to be more here. And then generate optimality cuts and continue. All right. So this is which one to use, right? And why? Again, this is only a beginning of this, so but at least it highlights certain things. All right. Many of them, which one to use? So to do this, we wanted to look at, we're going to end up looking at these limits. All right, and I'll tell you why in a little bit. So remember the phi divergence constraint is this big summation of the q omega and the phi of these ratios summed over all omegas, right? So if you look at one term of that for scenario omega, it's this one. All right? And we wanted to look at these limits. So as this goes to 0, which means this is positive, this is going to 0. This goes to infinity, which means this is positive, this is going to 0. Right? Oh, another thing is for the first case, we can look at phi of 0, or this limit. For the second case, because q becomes 0, we have to look at the limit of phi of t over t. Okay? And if both of them are 0, there's nothing happens because the divergence is 0. All right. So this is one case which actually people in robust optimization, when they solve these things, and some people, I think, practitioners complained in the sense that, look, I'm giving this problem something that I've observed. So it has a positive probability, right, in my nominal distribution. I've already observed the scenario omega. I solve my problem, and it ends up giving me, in the worst case distribution, it makes it probability 0. So it kind of suppresses it, right, from the scenarios that I consider, it suppresses it. And I don't want this to happen, for example. So this one, we need to look at, so remember, Q is 0, P is 0. If I go back, Q is positive, P is 0, right? We need to look at that limit. So that's what we do. If we look at this limit and somehow, and this is, by the way, geometric properties of the phi divergence, right? If this limit turns out to be infinity, and your phi divergence constraint said it has to be less than or equal to some rho, which is a finite number. If this is infinity, this will never happen, right? That phi divergence will never allow this to happen. So in that case, we say it cannot suppress scenarios. On the other hand, right, if this limit is actually finite, then the ambiguity region could allow this. It doesn't have to, but it could allow it. Especially if Q is sufficiently small, or depending on the value of rho, you can see this happening. So these phi divergences, we say, can suppress scenarios. All right? We also wanted to look at the opposite way. All right? Why not? So let's see what happens. So now, this is a scenario I have never observed. Right? I collected data. I've never observed it. But I'm throwing this in. Say, expert told me, here's a plausible scenario, but I'm going to throw it in my problem, and I'm going to let it decide. Well, maybe it's going to give me a positive probability when I do the min-max. It's going to tell me, you should consider this scenario if you want to be robust, if you want to be risk-averse. So this is what we call, from 0 to something positive, it popped scenario omega. All right? Suppression and pop. That's, all right? So, and then, remember, if that case, it's the other limiting thing. And the other limiting thing is basically you need to look at that limit, phi of t over t. And when we look at this, if this is infinity, just again, by the same reason, because your phi divergence constraints says each term summed up has to be less than or equal to some rho finite number. If this is infinity, this will never happen. So it will not allow you to pop scenarios. On the other hand, if this limit is finite, yeah, it can actually pop the scenarios. So this gives actually a classification of 4, right? Oh, and then last case, nothing, which basically gives us can suppress, cannot suppress, can pop, cannot pop, right? So basically, if you want the highest flexibility, you want to use one of these Phi-Divergences. You throw in everything in there, things you observed, things you didn't observe. You let the formulation, I want it to, I'll let it suppress, or I'll let it pop. Whatever happens, I'll let it decide. Or you say, hey, I've already observed something. I don't want it to suppress. I want it always represented. But maybe I can allow popping, so I'm going to use, you should use one of those things, right? And otherwise, like this one, cannot pop, cannot suppress. So in some sense, less flexible. In some sense, maybe that's what you want. And the other one is this one. All right? And there's these two things, 1, 2, 1, 2, out of the can suppress. So these are subcategories with respect to this optimization problem. And it's different ways of suppressing. All right? So we'll suppress scenarios in different styles. So the first one is, let me come back to this. So the first one is essentially individual suppression. So if you look at this one, and it's again with the conjugate relationships, if this is happening, if this is greater than negative infinity, there's a finite number, then it will suppress scenarios one at a time. All right? So again, looking at just the properties of the phi function, you can see how it's going to behave. So this will, as you increase your rho, your ambiguity region increases. It will suppress scenario, one of the scenarios. It will suppress the second scenario, third scenario, fourth scenario, one at a time. Versus this one, the limit is negative infinity. You're just going to go, 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 go. At some point, you're going to reach there. At that point, everything will be suppressed except for the highest cost scenario. Okay, so this is all of a sudden, everything except the most expensive scenario will vanish. So these are the Kullback-Leibler will do that. Modified chi-squared will do one at a time. So I go back here, Kullback-Leibler, modified chi-squared, and so on and so forth. So those are the two categories. All right, so there are some subcategories. And we wanted to say, like, okay, what kind of decision maker could use which type of Phi divergence? It's debatable, right? But so, for example, if you have high quality data, and again, if you believe that everything observed must be used in the model, that decision maker will prefer Phi divergences that cannot suppress. All right? On the other hand, if you have poor data, opinion rather than observation or some simulations, you don't trust your data that much, you can say, hey, I'll allow it to suppress. The popping, well, first of all, you have to put scenarios with 0 nominal probability in there. If you don't have to worry about popping. If you do, if you have strict observations and not that much, you don't want to mess it up, then maybe you don't prefer the popping case. But if you want to give it a lot of, different types of data, and you want it to, hey, assign a positive probability to them, why not? Throw it in there. So you can have this different types of Phi divergences will act differently. So here's a illustration. So the modified chi-squared is the individual suppression. This is the rho. So again, rho equals 0 is basically equivalent to solving the two-stage stochastic linear program with the nominal distribution. As rho increases, it becomes minimize the worst case scenario. It's the, because you consider all distributions, so the best thing to do is to find the worst one, assign probability 1 to that, everything else gets 0, and that's what's happening. So as you increase rho, the lowest cost scenario is suppressed. So it gets out of the picture. Now these are the probabilities of the other scenarios. At some point, this guy gets out of the picture. As you increase rho more, this gets out of the picture. And in the end, you're left with this most expensive scenario with probability 1. All right? So Kullback-Leibler, on the other hand, keeps essentially all the 4 scenarios here. And then, it lowers, like the lowest cost one will have a lower probability and so on and so forth. But at some point, right around here, lambda becomes 0. That's some numerical instability there. But at that point, it suppresses all of them. And then with probability 1, it's the most expensive scenario. So it suppresses all at the same time. Mm-hmm. Mm-hmm.
Does it mean that the probability is going to be some minimum value?
Yeah, so pop. So,
if it's not their spot, because if the people will be at least some bad. I think what if this scenario is a very bad? I want to include that, but it's not part of what I have observed.
yeah, so this is the popping. So it was 0 when you put it in. As you increase your row, it just starts to have positive probabilities, right? And at some point, it's the most expensive scenario, and everything else goes basically to 0, and this becomes, at the end, it will be like almost with probability 1, this guy, but at the beginning, you gave it 0. So it pops even like quite quickly, right? It will pop, and after that point, it will start to have positive probability, so much so that it has the highest one because it's the worst cost one, right? So, but if you had observed that scenario, this is the Burg entropy. If you already observed, so 1, 1, 1, 1, it still assigns it the highest cost probability. The other ones, they're diminishing because this is the highest cost, versus this one is the popping behavior. So to see this green one is 0 actually to begin with. So that's what it does. Yeah. And we have another result that basically says if you throw in scenarios, only the most expensive scenario will be assigned a positive probability. So otherwise, it will keep it at 0 level. All right. How am I doing in time? I don't know.
10 minutes.
10 minutes? Okay, let's see. All right. So we basically apply this to this water allocation problem. So just to give you an overall idea of what's happening, you must have heard all the issues about California, the droughts, the extended droughts. I mean, same thing in Arizona, but Arizona is definitely, has been dealing with this for so many years. They're ready. They use a lot less water than Southern California, which is super thirsty. And they use, so this is the lower Colorado River Basin, different states, and these are the, how much allocation is given and stuff like that, right? It's actually more than this, and Mexico is also, there's a lot of political issues here as well, all right? So there are different users, agriculture, hydroelectricity generation, municipal, industrial uses, etc. And the big question is, this water basically allows, right, Southern California to be there, farming to be done. Arizona, the population of more than 60% of the water in Tucson comes from Colorado River. Without this, population there would go down. I mean, same for California, Las Vegas, right? These things won't exist or not exist like what they are. But it's been experiencing a lot of droughts. How do we manage this, especially as some changes to climate and other things are expected, right? So this is a big question. What we're going to do is we're going to focus first on Arizona, and even within Arizona, we're going to focus on a really smaller area. But it's the same water, all right? Just to give you another idea of what's happening, so the Colorado River is here, but they bring it from this, there's a lake there, they bring it over to southern Arizona, right? Lake Havasu, it's more than 300 miles of these canals. This is the real picture. They carry that water. So in the old times, I think if you went on horse to get this to the Lake Havasu from there, like what, 5 days or 4 days on the horse to get this water, bring it over there just to go there, and then there's the return back journey. So they carry all of this. It's basically the largest and most expensive aqueduct system. And as I told you, like it covers more than half of Tucson's water, right? So, and this is Tucson, and then this is, even within Tucson, we're going to narrow down a little bit, because this is what, I've been working with Tucson Water, and this is what they're interested in because they believe the city is going to grow in that area, right? This is already established, everything is in there, but they expect a lot of new development here, and they want to look at what to do 40, 50 years down the line. And these lines that you see here are elevation lines. So there's like mountains over here, so the elevation is increasing, and that's how they divide the demand zones. So the water will come from here, and it will go to one zone up, because at every like sort of a junction here, as the elevation goes up, they create these pump stations, and they push the water up. It goes for a while, push the water up, right? That's how it works. And so these are going to be our demand zones. It's going to move in that direction. Oh, there's a highway here, I-10. So it will cross, no water pipes can cross that. So they basically have a north section and a south section and things like that. So you're going to see that we just created a model for this. All right. Oh, here's the thing. So this is that Colorado River Canal that I mentioned, that I showed you the picture of. Right, that canal that brings the Colorado River. It gets into this water reclamation facility. It gets treated there, cleaned up, etc. It's sent to the city, and then the water is used, and it's actually like all the way back taken to this wastewater treatment plant here. And then once water is cleaned, it's actually sent again and reused again. All right, that's how it works. So this is the blue water, is the Colorado River Central Arizona project, Colorado River water. So that treatment plant is the Hayden-Udall one that I showed you. There are some other things. It gets here, sent here. So the blue water is the clean water. At some point, it gets to this zone, demand zones in that area. And it gets used. That's the black water, dirty water, sent to the wastewater treatment plant. There's only one. It's a big one, only one in Tucson. And then after some other treatment, it's called the purple water. So it's not as clean as the blue one, but it's not dirty. So you can use it for some agricultural, watering the lawn and things like that, but you cannot use it for drinking, right? So purple water, and because it's water scarce area, you want to, it's operations research, scarce resource, you want to use it in the best possible way. And reusing water is one of the things. So one of the questions that they're interested in, so first of all, how should we, allocate this water among different users? Another thing that they're interested in is, this is a big water treatment plant, so it has, as you produce more scale, economies of scale, but they're considering, should we build a smaller water treatment plant in that new area? Is it worth it economy? That's another question. So as I told you, these are our elevation zones, which are the demand zones. These are pressure added. These are like potable water, like drinkable water, and you can use good water to do agriculture. But you can only use the purple water to have these, you cannot use it to drink it. All right, so demand will be satisfied in certain ways. And once it's used, it goes back to the, black water, goes to cleanup. That's how it works, and it goes between these things. As I told you, there's a highway in between, and nothing crosses, so they have the higher ones, the north ones, and the south ones. All right. So, and we just basically created a network model for this. And we talked, with Tucson Water, getting realistic terms and all these things. So each time period, we have 62 nodes, 102 arcs. And the arcs are, and we look at, well, I think we started it a little earlier, but now we're there, 2010 to 2015, we know what the demand is. And then we have energy cost, treatment cost, although we linearized everything just to make it easier. And we have discount rates and so on and so forth. The decision variables, how much water flows between each arc, how much to allocate, how much to store. This is really important for them because they want to figure out, they get the Colorado River and it's an inventory problem essentially. They want to store it as much as possible if there's population increases in the future or it gets too hot. So they'll use it for future. So they're risk averse in that sense. And they release some and then they lose some for evaporation, leakage. Approximately 10% of the water is lost when transporting. So this is generalized network flow. It's a multi-period generalized network flow. We created some scenarios, by the way, because there's a lot of uncertainty. So one of the things is the population of that region, right? So there are two studies that's been done. One is by the state of Arizona. One is by the county, specific county. And one of them estimates higher population. One of them estimates still increasing, but a lower increase. So we use those two population projections. We don't know what's going to happen. Colorado River water allotment scenarios. This is based on rules and laws. So if the lake mead level falls below a certain level, Arizona will get 10% cut. California will not, unless it goes below a certain level, right? I mean, so there are all these treaties. So we look at those, and by the way, we looked at a U.S. Bureau of Reclamation, did all these studies of when lake mead levels will go down using climate models, ice pack models. It's a really huge simulation, crazy model. So we use their things, and we basically estimated the probability that when lake mead will go down, or with what probability, stuff like that. All right, and we looked at how demand relates to climate, and we stick in also these 6 climate models developed by the earth scientists that I told you about that tell us like how much rain is going to be, what the temperature is going to be, you know, each year, each month, etc. So satisfied demand is in the constraints. There's a penalty cost for unmet demand. Right, that's which is important, yeah. So they actually buy water from, like, when there's scarcity, they buy water from other areas, which costs them a lot. So they want to avoid those. Yeah, and then cost of like transporting the water, treating the water, and so on and so forth. Right. So, and if you do all of this, it's 192 scenarios total. So not too big, but as I told you, these are the 2 estimates, studies that they've done, maybe even a little outdated here. One of them estimates a higher population, the other one lower population. As I told you, we looked at the U.S. Bureau of Reclamation studies and estimated these, and so on and so forth. There's a lot of details here, but I'm going to skip all the stuff. And the other thing is this temperature, precipitation, and how these relate to water demand, right? So this is really important because if the climate is changing, if it's getting hotter but maybe more rainy or less rainy, it's going to change the water demands. There's also a time change, especially in Tucson. What has been happening is there's so much educational stuff. People have been, this is a per capita gallons of use. As you can see, this has been dropping way too much. Tucson Water is actually unhappy about it because they sell less water, they make less money. So they are trying to make up with this, with the when they clean the water and send it to golf courses for irrigation, they actually make up the money that way. So like reclaimed water use has increased, and that's how they make up money. Otherwise, people have become so water conscious, they don't use water that much. And I mean, you can see like, you drop and it keeps going. So what we did is we created these regression models together with temperature and climate, etc. So this is one of the fits, but this basically continues that people will become more and more water efficient. So they will use less and less water per person, right? But this might not be true because there's a limit, right? You have to take showers, you have to drink and cook and whatnot. So we had another one, sort of a piecewise fit. It's not that linear, so we cap it, and we basically, this trend that goes down, we don't allow it to go down anymore after a certain point. And so this fit, the piecewise linear fit, will have higher demands because people cannot like keep lowering their daily use. All right. So here are the climate models. So we talked to some real people who work on these to get ideas. So these have different characteristics, and these are just more trusted models. And these have, like, there's this model C0, but then they have initial conditions like Earth's, like temperature, like this water models and whatnot. So you add on those, and then there's a greenhouse gas models that are added to it, and then once you combine those 3 things, it gives you temperature and precipitation things. All right, so these are the climate models. We also, to each climate model, we give 4 different greenhouse concentration paths. All right, these are again came up with this International Council on Climate Change and whatnot. So this is what it is. So this is the current path that we're on, the red one. So greenhouse gases are, going up this way, and if it goes on the same path, this is what's going to happen. And then they're talking about some treaties and etc. that says, like, okay, so this one is there's going to be more and more control It's going to increase, but at some point, we're going to be able to stabilize. And this one, it says, yeah, maybe initially we're going to be stabilizing a little bit more, but then it's, you know, economic development, etc. It's going to increase. We cannot control it that much. And this one is a super optimistic scenario that basically the Earth controls its production and the greenhouse gases, whatnot. But most people believe we're going to be on this path for a while. Yet again, this is what's recommended. They recommend to use these 4 paths, which maybe in reality you might even fall somewhere below here. It affects the climate models. You give it to the climate models, and then, yeah, so what they do is, like, if it's on this path, it gives you like a higher temperature, for example. Like, they have all these, as I told you, I don't know exactly, but partial differential equations and things like that. They all add these things and came up with stuff. All right. I told you they're also considering a decentralized water treatment plant here, and they're also considering, like, if the different levels of this water treatment plant, you can add more cost, but then once you do it, you can actually make it to the quality of potable water. You can even drink that water. So is it worth doing that? All right. So we have 4 different infrastructure options. One is no additional infrastructure. One is a decentralized water treatment plant. The other one is add to this an indirect potable reuse facility, higher quality water. Add to it reverse osmosis, higher quality water. It adds cost, but you can use that water for more purposes. All right. We use modified chi-squared distance. This is suppress one at a time. Kullback-Leibler, suppress all or none. Burg entropy cannot suppress. We didn't consider popping because in this case we didn't put any 0 probability scenarios. All right. So here's the total cost. Oh, and then we changed the rho with respect to 90%, 95%, 99%. Obviously, as you have higher rho, the cost become increased, right? And this is modified chi-squared, Kullback-Leibler, and Burg. And this one actually gets somewhat lower than the one that cannot suppress and the one that suppresses none or all or none. Here is another look at it. These are these greenhouse concentration paths. This is the path that we're on, right? And you can see it has the higher, because you're doing minimax, this is the higher costly one. It's going to assign more. These are the probabilities it assigns of the different climate models. So it assigns more to this highest path. And the second one is this 4.5. And then to the lowest one, it's the really optimistic scenario gets the lowest probability of them all. Okay? And other thing, we looked at that value of additional data. So that condition is satisfied for every low population scenario. Remember, we have a high population and low population for future population projection. So if you increase your belief on the low population, you're going to rule out the worst case. Linear fit scenario is like people become more and more and more efficient in their daily water use. So that's going to satisfies the condition. And no high population and piecewise fit, that's the higher demand. High population and higher demand per person scenario doesn't fit. So those are the things that you need to watch out for. These are bad scenarios and these are good scenarios, so to speak. And that condition gives you that quickly. Even more, so predicted shortages by infrastructure option. I don't know if you can see. This is no infrastructure. This is the high population, high demand per person. This is like the worst case. The highest cost will be here. So do not take as many showers. Take less showers. It makes a difference. All right. And then, you know, like if you have low population but high demand per person, even with that, you pull it back, right? And then these are the lower populations. This is low population, low demand per person. So if you, I mean, human demand makes a huge, huge difference. So if you add reverse osmosis, the shortages become less. It goes, none wastewater treatment plant, I'm sorry. If you add a decentralized water treatment plant, you reduce some of the shortages there. if you add this higher quality water, you can meet other water demands. So you again reduce the shortages. Reverse osmosis doesn't make that much of a difference. I mean, the colors are hard to see here, but you definitely move from this one to all the way here. So it almost becomes like this. So by adding this decentralized treatment plant, you actually have a better control of your water demand. Yet again, when we look at the cost of it, right? No infrastructure, these are the costs. If we add water treatment plant, the cost overall will decrease by, say, 14 million. If you add on top of it the IPR, higher quality water treatment, further decrease of, like, there's a big jump here, 24 million. And this one, a little bit more, additional 10 million, right? And we looked at, is it still worth doing this economically? And so here's the key. They assume $800 per acre feet shortage cost. At this cost, no infrastructure is worthwhile, because if you do the water treatment plant, savings of 14 million, but it's going to cost you $55 million. Okay, so even at that, so just reducing human demand is the most effective way of dealing with this. But here's an issue. I mean, this model has a shortcoming, obviously, because this water shortage cost depends also on climate, depends also on the current water levels, etc., right? So this is true. They have paid in Yuma several years back $25,000 about there, $25,000 per acre feet when there was an extended shortage. So, you know, it's an extreme point in there. But just using this, I'm not sure how realistic this is, but there's a huge difference between like 55 and 14 million. So there needs to be better modeling of this shortage cost, right? And tie it to climate, tie it to per capita demand use, and so on and so forth. With that, it will be more worthwhile. So the break-even cost, so we calculated, like, so if we do, say, with Kullback-Leibler divergence, instead of $800 per acre feet, if it goes up to a little bit more than 2,000, then having a decentralized water treatment plant is going to break even. If you go to 3,000, then adding the additional capacity of IPR will be also break even. All right, that's what I have. So just to wrap it up, summarize. So we discussed stochastic programs with ambiguous set of distributions using Phi-Divergence. And we investigated what happens as we increase, add more data, provided some classification of the Phi-Divergences and, you know, what type of Phi-Divergences could be used by which decision maker. A decomposition-based algorithm to solve this problem, and we applied these things to actually a real-world problem in water. So these are my future work. Extension to multi-stage is still future work, right? Extension to continuous distributions, further refinements of the classification will be really nice, and like more examination there. So somewhat there are different ways of doing this, right? So one of them just came out, like the Wasserstein instance, what happens when you use that instead. And there's some improvements, as I told you, in the water study and the multi-stage. So we did a two-stage version of this water problem. I also have multi-stage models, but those are stochastic. We do SDDP type of stuff with the multi-stage one, not the ambiguous one yet, because it needs to be more developed. So my student who worked on this, the Tucson water, we had a lot of help from people, and I'm really grateful for that. And also all the climate models, people that share their models and funding. So thank you very much.